Next, we will discuss the usage of the dot convention. Let's review the problem in the beginning of this lecture. We first mark dots for the coil. Assuming that the upper left is a dot, then the direction of the magnetic field is clockwise. So the upper right terminal needs to be a dot. According to the derivation in the last lecture, we can know that if the current of coil 1 flows from the dot, and the reference direction of the voltage on coil 2 is from the dot to another terminal, then U21 equals M times dI1 over dt. For the second question in the previous lecture, we also said the upper left is a dot. Then the direction of the magnetic field is also clockwise. So the lower right needs to be set as a dot for the second coil. If the current of the first coil flows into the dot convention, and the reference direction of the voltage across the second coil is from non-dot to dot, then we can get that U21 equals minus M dI1 over dt. Or conversely, in the second coil, if the reference direction of the voltage is from the dot to another terminal, we can get that U equals M dI1 over dt. What does this help? You see, if two inductive coupled coils have been set the dot convention based on their winding directions by the manufacturer, then we don't need to know their internal winding directions in practical applications. We can determine the positive or negative value of the inductive voltage only by the dot convention. Specifically, that is to say, when the current of a coil flows into the dot, the direction of the voltage across another coil is from the dot to another terminal, then the induced voltage is M dI1 over dt. Of course, if the direction of the voltage across another coil is from non-dot to dot, then the induced voltage is negative. Well, we do two exercises. For the first one, the current flows from the dot of coil 1, and the direction of the voltage across coil 2 is from dot to another terminal. Then we have U21 equals M dI1 over dt, obviously. Do you find? We don't need to know the winding directions of the coil 1 and 2. As long as we have the dot convention given by the manufacturer, we can determine the positive or negative value of the induced voltage. If the reference direction of coil 2 is defined from non-dot to dot, then we know that U21 equals negative M times dI1 over dt. Next, we discuss a case that the two coils all have currents. For dot convention given in the figure, it not only has self-inductive effect on coil 1, but also has mutual inductive effect due to the current of coil 2. So it has such a KVL equation for coil 1. The right path has two items. For self-induction item, we know that U1 and I1 are associated reference directions, so we have. From the viewpoint of the mutual induction, the current of coil 2 flows into the dot, while the direction of the path is positive above and negative below, so the induced voltage is positive. We use KVL for coil 2, the path is like this. Using similar method, we can get that. Now we look at another example. In this example, the dot convention is not the same as the first one. The KVL of coil 1 also has two items. We write them respectively. The first item is positive because of the associated reference directions of U1 and I1. For the second item, the current flows from the non-dot terminal of coil 2, and the voltage is from dot to another terminal, so it is negative. The KVL path is like this for coil 2. We first discuss the mutual voltage. The current of coil 1 flows into the dot, while the direction of the voltage is from non-dot to dot, so the mutual voltage is negative. The voltage and the current have associated reference directions for coil 2, so there is a positive self-inductive voltage. For such a coil, if we mark its reference direction of the current in reverse, what will be the result? The self-inductive voltage has no change for coil 1, but for mutual inductive voltage, now the current flows from the dot. Then we write the KVL equation according to this path. That is a positive mutual inductive voltage, like this. For coil 2, we first consider the mutual inductive voltage. The current flows into the dot, and the direction of the voltage is from non-dot to dot, so the mutual inductive voltage is negative. The voltage and the current are non-associated reference directions for coil 2 now, so its self-inductive voltage is negative. When we discuss the case that both coils have currents, the dot convention is necessary to determine the positive or negative of the mutual inductive voltage, and the directions of the voltage and the currents of the same coil is also needed to determine the positive or negative of the self-inductive voltage. About the mutual inductance, our discussion are all time domain expression. Of course, under sinusoidal steady state, they can be converted to the expression in phasor. We take left circuit as an example. Its phasor relation should be like this. Thus, the discussion on dot convention can be extended to the analysis of SSS seamlessly. Well, that's the end of this lecture.